Today's episode is part 2 about color and the brain. Why did royals wear purple? It's not accidental, and if you rewound history 10,000 years and ran it again, you'd find exactly the same outcome. So what's going on? And how do we see colors that our recent ancestors never saw in their lives? Why can't you imagine a new color? Are there in fact new colors that you could see? Yes, and I'm going to show you how to do that. Can you lose your color vision? And what does any of this have to do with language or culture, or why the military likes colorblind people for a particular task? And why I suggest that the cultural history of Thailand was influenced by one single unknown neurodivergent. Welcome to Inner Cosmos with me, David Eagleman. I'm a neuroscientist and author at Stanford, and in these episodes, we look at the world inside us and around us to understand why and how our lives look the way they do. Today's episode is part 2 about the absolutely amazing and often underappreciated topic of color. And if I do my job right, this is going to allow you to see the world with totally fresh eyes. So we're going to start with a quick catch-up from last week so we can continue this incredible story about color and the brain. Last week, we talked about the fact that color is not a property of the physical world, but it's a creation of the brain. Color doesn't exist in light itself. Light is just electromagnetic radiation of various wavelengths, and our brains interpret those wavelengths by constructing the experience of color. This private interpretation of color begins in the retina with a special type of photoreceptor cones, which detect wavelengths and come in 3 flavors, sensitive to short, medium, and long wavelengths, which corresponds approximately to red, green, and blue. The brain then processes patterns of activation across these cells to produce the experience of color. And last week we talked about color constancy, which allows us to perceive colors as stable despite the changing lighting conditions, something that we see all the time in visual illusions. We also talked about evolution. For example, we humans have 3 types of cones, giving us trichromatic vision. But this is a rare trait among mammals, most of whom are dichromatic, meaning they have 2 types of cones. And this is likely because of a nocturnal bottleneck, where during the age of dinosaurs, the ancestors of mammals had to avoid getting stomped on and eaten, and so they scampered around at night and got better night vision, but lost some of their color vision. Now, humans and some other primates re-evolved trichromatic vision, possibly not just for spotting ripe fruit, but for social reasons, detecting subtle changes in skin coloration due to emotions. But in any case, lots of our neighbors in the mammalian kingdom can't see red and orange, which is why deer hunters wear orange vests, because that allows the hunters to see each other clearly, but the deer just can't see them. And finally, we saw how other species like bees and snakes and mantis shrimp, they presumably perceive the world very differently because their eyes pick up on ultraviolet light or infrared light or polarized light. And if you tune into last week's episode, you'll hear lots of other stories about how color serves many functions like camouflage or warning or mating signals or deception or emotional communication. Now we're ready to continue our story this week. So let's start with something that I think is amazing, which is that we see so many more colors than even our recent ancestors did. This is not because of a change in our biology. It's because our current collection of technologies can generate so much more. For example, your great-great-grandparents never saw a lot of neon or the bright ultra-red of a Tesla or the blaze orange of a caution sign on the road, but we see these colors all the time. Now, I want you to try this. imagine a new color. Go ahead. Okay, you can't do it. The fact that you can't do it is very revealing, and it's very important because it illustrates for us the fence lines of our perceptions, beyond which we just can't walk. And by the way, if you could envision a new color, you wouldn't be able to explain the sensation of it to another person. For example, you have to experience purple to know what purple is. There's no amount of description on a podcast or in a textbook that's ever going to allow a totally colorblind person to understand purpleness. Here's an analogy just to make this clear. Try explaining vision to a friend of yours who is born blind. You can try all you want, and your blind friend might even pretend to understand what you're talking about, but it is a fruitless attempt because to understand vision requires experiencing vision. And that's the same with experiencing purple or canary yellow or cobalt blue. You have to experience it to know it. There's no way to describe it. Language is just a way of tagging shared experiences. And if it's not shared in some way, no amount of language will do the trick. Okay, so let's come back to the idea of whether you will ever have the chance to see a new color. Well, it seems pretty clear that the answer is no, because the space of possible colors that humans can see are pretty well represented in our world. But under special circumstances, you can see new ones. So first, let's start with what are known as impossible colors. These are colors that are outside what our cones can put together. For example, you can't have a reddish green or a yellowish blue. These are combinations that the visual system just isn't wired to perceive simultaneously. But under certain conditions, using tricks in the laboratory, some people do report glimpsing these colors. These perceptions are fleeting, but they hint at the boundaries and the flexibility of color perception. So here's something that you can try easily. Let's say that you stare at a square that is cyan in color, and you just stare at that for 20 or 30 seconds. Then if you look over to a white piece of paper, you'll see an orange afterimage. Okay, fine. But now, after staring at the cyan, try looking over at an orange piece of paper, and you will see what we call hyperbolic orange, which is an orange so orange that you never can normally see that. Now, there are a bunch of ways to see impossible colors. Here's one. Stare at a yellow square for a while, and then look at a piece of paper that's black. You'll see what is called Stygian blue, which is a blue that is darker than black. Or stare at a green square for a while, and then look at a white background, and you'll see what's called self-luminous red, a red that is brighter than white. These are some ways to see outside the normal fence lines of color, and I'll put demos of these on the show notes at eagleman.com. Now, there are other ways to see new colors that require doing so in the laboratory. I'm going to come back to that near the end of the episode when I'm going to talk about the future of seeing color. But for now, I want to mention something else, which is the issue of seeing data outside the normal visual spectrum that we can see. For example, it might sound impossible to see in the ultraviolet range, but it turns out your photoreceptors can do that. It's just that the lens of your eye blocks out UV light. But then something was accidentally discovered in the last couple of decades. A lot of people go in for cataract surgery and they get their lens exchanged for a synthetic replacement. Your natural lens blocks UV, but the replacement lens does not. So patients found themselves tapping into ranges of the electromagnetic spectrum that they couldn't see before. I wrote about one guy in my book Livewire. His name is Alec, and he got a lens replacement for his cataracts, and he now describes a lot of things that he looks at as having a blue-violet glow that other people just don't see. He noticed this the day after his cataract surgery when he was looking at his son's Colorado Rockies shorts. Everyone else saw the shorts as black, but he saw them with a blue-violet sheen. When he put a UV filter over his eye to block out the UV, he saw them like everyone else. Here's another example. When you look at what's called a black light that's turned on, you don't see anything, but Alec sees a bright purple glow. So this gives him a new superpower, seeing past the normal spectrum of colors. Alec has different kinds of experiences than we do when he looks at sunsets or gas stoves or flowers. Now I want to flip the question to examine the other side. Could you lose your color vision? Yes, it's rare, but it happens, and it's called achromatopsia. People with this condition see the world entirely in shades of gray, as if life were filmed through the lens of an old black and white movie. It's not just muted color or red-green confusion, it's the complete absence of color perception. Just imagine this. The vibrant world that we all take for granted gets rendered by your brain in a perpetual grayscale, where even a rainbow is just a smooth gradient of light and dark. Now, the thing I want to note is that achromatopsia results from brain damage, specifically to a region called area V4 in the visual cortex. Because color vision doesn't happen in your eyes alone. While the cone cells in your retina detect different wavelengths of light, the experience of color is assembled in the brain. And one of the key regions responsible for putting those wavelengths together into color perception is this area V4, located in what's known as the ventral visual pathway in the brain. The point is, if this area is damaged from a stroke, from head trauma, from a brain tumor, the person gets this cortical color blindness. The eyes are perfectly healthy, but the brain can't interpret color signals anymore. So the person experiences the world in grayscale. So this once again illustrates the simple but critical point that color is a construction of the brain, and you have to have all the right pieces and parts running, or else you can see just fine, but you can't see color. Now, some people, of course, are born colorblind, but not because of brain damage, but instead because they don't have some of the types of cones in their eye. As a reminder, most people are born with 3 different types of cones, color photoreceptors, but some people are born with only 2 types, or 1 type or none, giving them a diminished or no ability to distinguish between colors. Now, the military excludes colorblind soldiers from certain jobs, but they have come to realize that colorblind people do have a secret superpower. They can spot enemy camouflage better than people with normal color vision. Why? Because they're better at distinguishing between shades of gray. This is because they have the same amount of visual cortex at the back of their brain, but fewer color dimensions to worry about. So they're using the same cortical territory, but for a simpler task, just grayscale instead of color. And this gives them improved performance in distinguishing very subtle differences in brightness. So although it would be a real bummer to be colorblind, there are some advantages as well. So now let's return to color. Everything we've talked about so far is a reminder that color is not just about the electromagnetic radiation hitting the eye, but about what happens in the brain. And one very good example of that is something I've talked about before, synesthesia. This is a brain phenomenon in which color blurs with different concepts. A typical synesthete will perceive letters or numbers as having fixed colors, like A is always red, or the number 7 is seafoam green. And it can commonly be with weekdays or months, like Wednesday is indigo blue, or August is yellow. Now, it's not a hallucination, but to the person, it's just self-evidently true that that's what that letter or number or weekday or month is. Of course, it's purple or yellow or green. So I've studied synesthesia in my lab for many years because it's such a good inroad into conscious experience, and also the differences between one person's experience and another's, and the differences between people's experiences on the inside when they're perceiving the world. If you're interested in synesthesia, please listen to episode 4. But for now, I want to zoom in on the issue of colored weekdays, which is a common form. The thing I want to emphasize is that the color palette ends up being different for each synesthete. So one person person might say, oh, Monday is clearly green and Tuesday is purple and Wednesday is yellow. And a different synesthete has a different color palette. Now, I've studied literally thousands of such synesthetes, but here's something I just learned that really surprised me. I learned that in Thailand, there's an ancient tradition in which each day of the week has a corresponding color rooted in Hindu-based astrology. So Monday is yellow, Tuesday is pink, Wednesday is green, and so on. Apparently, these colors are tied to planetary deities, like Mars for Tuesday is associated with pink, Mercury for Wednesday is green, and so on. And traditionally, it was believed to bring luck if you wore that color or used that color on the corresponding day. This apparently used to be very common in Thailand to wear the right color every single day. Today, it's a little less common. Now, you can probably guess what I'm wondering about, which is where did this colored weekday idea come from? Well, if you consult any Thai book on this, they'll say it comes from the colors of their deities. But of course, gods don't really exist, and if they did, it's not obvious they would have colors or that anyone would have seen those colors. So my suspicion is that if we really did get to the bottom of this very ancient history, we'd find a very influential synesthete at bottom. Someone who said, well, of course Tuesday is pink and Wednesday is green and so on. And because of some cult of personality, it stuck. And millennia later, kids are still told that this deity is this color, so that day is the color and you should wear that shirt. And so, like all stories with cultural momentum, people accept it. Why? Because everyone else accepts it, and for thousands of years. So there must be something to it. But that something, I suggest, is a single influential synesthete whose quirky neural network determined what everyone wore for hundreds of generations. So if you ever think neuroscience doesn't affect culture, take that. And on that topic of the intersection between neuroscience and culture, I want to zoom the camera out to see what happens when lots of humans start talking together about color. So we're going to turn now to language. For most listeners of this podcast, we look at a rainbow and divide it into red, orange, yellow, green, blue, indigo, violet. But not every culture divides the spectrum the same way or sees the same number of colors. In some languages, there is no distinct word for blue. In other languages, green and blue are considered shades of the same color. As an example of the kinds of differences here, the Himba people of Namibia group colors differently from English speakers. They have multiple words for what we call green and none for what we call blue. Even ancient texts reveal this difference in color vocabularies. So in Homer's Odyssey, the sea is never described as blue, but it's described as wine dark. Scholars have long puzzled over this poetic phrase. Was it a metaphor, or was it that the ancient Greeks didn't categorize blue the way that we do? Blue appears almost nowhere in ancient Greek language, and where it does, it's often ambiguous. Why? Well, in ancient Greece, there were few blue dyes or paints. And by the way, blue animals are extraordinarily rare in nature. So while the Egyptians used a synthetic pigment, which we call Egyptian blue, the Greeks didn't use or produce blue. So it meant that blue was less present in their daily life or in their clothing or in their art. And the thought goes that it was therefore less common in the language. In the same way that cultures on the equator have fewer words for distinguishing types of snow than do northern cultures. Now, zooming out a moment, there were two researchers, Berlin and Kay, who proposed that even though language might have different color terms, they all follow a predictable order in the development of these terms. In other words, the first two terms to appear historically in any language are always black and white, or dark and light. Then comes red. Then when cultures get more cultures, they introduce green or yellow. Only later do you get things like blue and brown and more nuanced shades like pink or orange. The hypothesis is that this progression matches the salience of colors in the environment. The contrast of light and dark is really important. The presence of blood, the ripeness of fruit, the necessity of distinguishing between plants. So it's only when societies become more complex and encounter more dyes and materials and artistic traditions, then you get new color terms emerging. So different languages have different color terms, and one idea that has emerged is called linguistic relativity, which is this notion that the language that you speak shapes how you perceive the world. The idea is that although all people can see blue, if your language doesn't label it distinctly, you might not really pay attention to it as a separate category. And this is indeed what a lot of cognitive science studies have found. Your language shapes, at least a little bit, your color distinctions. For example, the Russian language has distinct words for light blue and dark blue, and when Russians are tested on their ability to distinguish shades of blue, they're faster at spotting the difference between light and dark blues than English speakers who use one word for both, blue. In other words, Russian-speaking brains process the difference more quickly, suggesting that having a word for something helps you see it. If your language has more precise blue terms like Russian, you can distinguish shades faster than languages that don't, like English. And you can see the same story in babies. Infants can see color long before they learn to speak, but once they acquire the words for specific colors, their ability to distinguish them improves. Language tunes the brain to attend to specific aspects of the scene. So if the Greeks didn't have a strong word for blue, they might have grouped it with other colors like green or gray and not really noticed it as blue. The Greeks didn't lack the ability to see blue, but in their culture they didn't isolate it with language. Likely because blue was rare in their environment and their language hadn't evolved to distinguish it clearly. So when Homer describes the sea as wine dark, it's not because he was colorblind, it's because the way his culture saw and named colors was a little different from ours. And by the way, this issue about the Greeks and blue, the same is true of many ancient languages, including Hebrew and Chinese and Japanese. And in modern studies, we can look at the Himba people, who, as I mentioned, have multiple words for green and none for blue. In experiments, they can easily distinguish green shades that we Westerners struggle to tell apart, but they find it difficult to pick out a blue square from a field of green. Now, we've been talking about biology and language, but what's fascinating is how this private phenomenon of color takes on cultural meaning. So there are a million examples of this. I'll just do a quick whistle-stop tour. So just look at the way we organize our world through color. We have red states and blue states. We have green energy. We have black markets. We have white lies. Color becomes shorthand for complex social and political ideas. Even our moral frameworks become color-coded. You've got the white hat and the black hat in the old Westerns. You've got the white dove of peace. You have the red devil of temptation. And colors very commonly come to signal identity and allegiance. You have teams and uniforms that define us versus them by color. Movements adopt symbolic palettes, so the suffragettes wore white and green and violet. AIDS awareness uses red. Environmental causes green. You see rainbow flags at pride parades. You see orange worn by anti-gun violence advocates. So in this way, when we look around, we see that color comes to serve as a quick symbolic flag. Now, not surprisingly, there's nothing fundamental about these associations, and therefore they aren't static. So in the 1800s, pink was considered a strong masculine color related to red. Blue was seen as delicate and feminine. These meanings flipped in the 20th century, and it had to do with shifts in fashion and marketing and cultural signaling. Color, like language, evolves, and political colors vary. So you've got red for the left in Europe, blue for conservatives in the UK, and it's reversed in the United States. What I recently read is that the colors in the United States, blue for liberals and red for conservatives, this got nailed down just around the year 2000, when the major television networks started using this as a visual shorthand for liberal and conservative. And that's how it got crystallized into public consciousness. I don't really know the history of this, but I suspect that in the decades of black and white newspapers, it was easier to use a donkey and an elephant to distinguish the parties, and only when color television became ubiquitous did it make sense to introduce a quick color flag. Okay, so now coming back to cultural messages, what is conveyed by a color depends on your local context. In Western traditions, white is associated with purity and innocence and weddings, but in many Eastern cultures, white symbolizes death and is worn by mourners. In South Africa, red can be a color of mourning. In Brazil, purple is reserved for funerals. I'll give you another example. Red, which in the West can symbolize danger or passion, is associated in China with celebration and joy and luck. A bride in India might wear a bright red sari while a Western bride walks down the aisle in white. So the point here is that cultural color symbols are learned. They're not innate. They are built from shared stories and traditions and rituals. Now, despite this variation as far as what color means what, sometimes there is a logic to it. Now, one thing I've always found fascinating is that purple is always associated with royalty. Why purple? Why not orange or yellow or something else? Well, it turns out this started in ancient Rome with a dye called Tyrian purple. This was a deep hue and it was unlike any other dye that was available at the time, and the color became irreversibly associated in their society with nobility and wealth and the divine aura of emperors. But what was so special about it? Well, Tyrian purple was made from the mucus of a specific sea snail. So producing just 1 gram of dye required thousands of snails and days of labor. In other words, the dye was extremely labor intensive and therefore very expensive. Only the wealthiest could afford it. And so that's how a particular color came to represent something. What's interesting is that it started off as an economic issue, but by the Roman imperial era, the association between purple and power was codified in the law. So you weren't allowed to wear garments dyed in Tyrian purple unless you were an emperor or a high-ranking official. Apparently, you could be cited with treason if you did this. So purple started out as expensive, but it eventually became politically exclusive. And by the way, this wasn't just Rome. In various societies, you find these laws called sumptuary laws, which are like dress codes backed by law. And these are there to restrict which people can wear which colors. For example, you find the same kind of sumptuary law in Elizabethan England, where only royalty and nobility were allowed to wear certain dyes. The idea with these laws is that they're designed to visibly maintain the social order. So again, colors become a shorthand label for larger concepts. Okay, so we've talked about this terrific history of colors where certain colors came to have particular meaning. But then what happened was the invention of synthetic dyes in the 19th century. And suddenly you had this explosion of vibrant hues that became accessible to the masses. The first synthetic dye was mauve, and that was discovered accidentally in 1856. And that sparked a fashion revolution because what followed was an explosion of new hues, artificial magentas and bright greens and vivid blues and optimistic yellow and eventually drunk tank pink and ultramarine and atomic tangerine and NATO green and millennial pink and safety orange and on and on. So the world in a very short period of time became much more colorful. So that's the recent history of color, but I'm also interested in the flip side question, which is, what is the future of color? Because we're beginning to enter an era where color doesn't have to be limited to what the eye evolved to see or the dyes that we're able to make. First of all, we're well beyond dyes now because our modern technology has changed how we see color. We have digital screens that use RGB, red, green, blue. and they mix light instead of pigment, and any typical screen now displays over 16 million different colors. But the future of color is going to go way further than that. As a simple example, we've talked about how color can be used to label information. So we can use augmented reality glasses to map colors on the fly. Imagine that you are in a factory where some machines are hot and some are cold, and you just map the temperature data onto red or blue so that you can see the temperature at a distance. And of course, it doesn't have to be temperature. It could be anything like how full the tanks are, or how many cycles per second are running on the chips, or whatever information you need to carry, you can encode that in color. But it gets better than that, because new technologies are actually expanding the colors that you can see. You can zap particular photoreceptors and not others to see more saturated colors than you've ever seen before. So at Berkeley, my colleagues have pulled off a new project where they bypass your eye's normal machinery and paint directly on your retina with light. And what they can create is a brand new color, a literally never before seen hue, a super saturated blue-green that the research team calls OLO, O-L-O. What does OLO look like? So picture the most saturated teal that you can imagine, then crank it up past anything nature offers. The green of a laser pointer feels dull in comparison. Here's how it works. Using very tiny doses of laser light, they individually target photoreceptors in your eye. They don't just hit one photoreceptor, but an entire constellation of about 1,000 cones. It's like they're painting on a tiny movie screen the size of your fingernail. They're painting with light directly on your retina. The key is that normally, each one of your cone cells responds to different wavelengths, short, medium, or long, but there's so much overlap in the green and the red cones that it's been impossible to isolate just the green cones, the medium wavelength cones. But using this technique, that's what they can do. So when only the medium cones are stimulated, the result is OLO, a color that doesn't exist anywhere in the natural world. Now, if the laser jitters accidentally so that it activates nearby cones, the illusion collapses and you're back to just plain green. And that shows how fragile this new color really is. So this is how we can unlock entirely new sensory experiences. Your brain is seeing something it never evolved to see. And that brings us back to a deep question in neuroscience. What happens when you feed the brain new information it's never had before? And we see that the brain just makes up a new color, OLO, which is not born of the sun or of nature, but of precise cellular targeting in the lab. And so the possibility is there that maybe we're just at the beginning of what human perception is capable of. What amazes me is that we can't imagine new colors, but once we've seen them, then it's part of what we can imagine. And this tells us that there's always more beyond the fence lines of our internal models, which is what my next book is on, which will hopefully come out next year. Okay, now I want to get back to how science is going to expand our perception. I think it's inevitable that genetic tools are going to make it possible someday to modify our eyes to detect new parts of the spectrum. So for example, we'll someday genetically give humans new flavors of photoreceptor cells. Could you add a fourth type of cone to the retina? I told you last week about tetrachromacy, in which a tiny fraction of women see hundreds of millions of colors rather than, let's say, 1 million, which is what most of us can see. And this is because they have a genetic mutation that gives them a fourth cone type. So you could genetically engineer tetrachromacy like this. But you could also engineer a fourth cone type to see beyond the current limits of visible light. Imagine your great-grandkids being able to see magnetic fields like soft glows of color, or to see other things that are totally invisible to you like infrared or ultraviolet like snakes or bees do. This would just be an extension of the way that our brains use colors as a way of tagging information in the world. But now we'll be extending our perception beyond its biological history. So let's wrap up. color feels like one of the most real and immediate and obvious aspects of our experience. We fall in love with somebody's eyes. We remember the yellow walls of a childhood bedroom. We mourn in black. We celebrate in white or red or gold. But what we've seen in this episode and the last is that color isn't fundamentally a property of the outside world. It's a creation of the brain. There's no color in a photon. There's just energy, just wavelength, and your retina receives that input, and your brain compares and contrasts it with other inputs, and out of this massive internal computation, you experience something radiant and vivid. And by the way, it's quite personal, which is why a blue and black dress can divide the internet. So the next time you admire a sunset or choose a shirt or linger over a painting, remember that you're translating physics into a subjective interpretation. Color is a collaboration between the external world and your internal model of it. It's where physics collides with perception. Finally, I just want to revisit how crazy I think it is that we see colors every day that Julius Caesar never did. And not just Caesar, but Shakespeare and Pocahontas and Abraham Lincoln, everyone, until the proliferation of synthetic dyes and eventually digital screens, the world before us just didn't see that many colors. Colors that we get to see every day and typically don't even consider the size of the palette that we get to appreciate. So spend a few minutes today just looking around and thinking about the millions of hues that you're looking at. Look at the fashion around you, the clothing, the car colors, the paints, even the annoying stuff like the advertising posters and the road signs. Even these are quite extraordinary when you look at them through a new lens of appreciation. And I'm really fascinated in thinking about how biotech will reach into new color territories that we can't currently imagine. I told you about the new color Olo, made by zapping specific photoreceptors and not others in the lab. Just imagine what things are going to look like in a century. Our descendants might feel as sorry for us and our pitiful little spectrum as we feel for our distant ancestors. Go to eagleman.com/podcast for more information and to find further reading. Join the weekly discussions on my Substack and check out and subscribe to Inner Cosmos on YouTube for videos of each episode and to leave comments. Until next time, I'm David Eagleman, and this is Inner Cosmos.